Good morning. Welcome to Krishna's class. We have, in our last lecture, explored two cornerstone inequalities, namely the holders inequality and one of its consequences, or a major consequence, is the Minkowski. Now we are in a position to look at or construct the so-called LP spaces. So let us explore what exactly these LP spaces are. Okay? So that is our major task. We wanted to explore this space. First of all, set the space well defined, and after that, more deeper exploration of this structure. Okay, so we begin with, so let X be an arbitrary measure space, which means you have X and a sigma algebra of subsets already set on that with a measure so mu denotes the measure. So what we have is something like this: X, this is the sigma algebra, space is now set. Now on this we define the following. In fact, you can here 0. Everything is well defined. A complex valued function defined on, it's a complex valued function defined on X, defined this is the notation that we use throughout. We denote by what is called the norm of F, or the P norm of F, one upon two. Now you can see that this is well defined, right? And we designate by LP mu, this is the notation that we use, the set of all F complex measurable on X, and such that is less than infinite. It's finite. Okay. So we are restricting to all those functions F which is complex valued measurable on Complex means complex value, measurable and measurable functions on X, and such that norm f p is finite. Now this is the important. We designate this by 2. So we shall say that norm f p is called at this stage it only means it's a concept of length of okay. Now we look at some standard examples. We take x to be equal to rk and mu the Lebesgue measure. Then we look at LP mu. We shall often designate this by LP. Now understood that the Lebesgue measure, that is what we do. But instead of so we are looking at all complex valued functions, complex valued measurable functions defined on RK. Okay, with the property that the norm of f, p norm of f is finite. That's the class that we teach. Okay, so that's one example. A second example, okay? If u is a counting measure, on a set A, the corresponding LPA is designated by LP, or simply LP. This is something familiar. Okay. So what are the elements of LP? Suppose A is countable. Then suppose A is countable. Then an element of LP may be denoted by components psi n, where psi n is, or it's a complex sequence. What is happening is, see, A is a countable set, therefore its element can be designated as the first element, second element, and so on. Okay, so it's assume that it is something like say Tn or something like that. Then you can write x as a function x as x Tn, x evaluated at Tn, and x evaluated at Tn is going to be a complex number, and put that that sequence of, so you have a automatically a sequence of complex numbers, and this is what it is. And with the property not completed, it's just a complex sequence, what we have already written, but to also put the condition that norm of x or the p norm of x is finite. So that's our that's what we want to write. And equal to and we insist that this is finite. Okay, so we insist that this is for every x. So we want to consider an extreme situation of this, namely when p takes the value infinity. So to consider this, so these are all for 0 less than p less than infinity. Then we define what is called essential supremum of the function. Essential supremum. Suppose t is from x to 0 infinity. We are taking a extended real value function is measurable. That means all open intervals, pullback of all open intervals by G is a measurable set. Okay. So we designate by S set of all alpha belonging to R such that mu of What is this? Here we are taking the function. See, suppose this is alpha. So this is from alpha to infinity. So if you are taking a function here, then you see that this is the portion that comes out as f inverse of infinity. I mean, it could be as very weird. For instance, you take the function g to be the suppose you take g to be equal to the characteristic function of q, the characteristic function of okay. So it takes, see, in that case gx equal to 1 when x is rational, equal to 0 to complement. This is the function. And you can see that, suppose you look at this one. So look at this one, mu of alpha infinity, mu of alpha infinity will be, sorry, g inverse of alpha infinity, g inverse of alpha infinity will be essentially empty set whenever alpha is greater than or equal to greater than or equal to 1. When g inverse of will be equal to q if alpha lies alpha belongs to 0 1. Okay, and it is going to be the whole of R if this is going to be I'll put it this way. Okay, this is what. Okay, and you know that as such the measure of this is 0. The measure of this is infinity, and the measure of this one is 0. Because q is, although non-empty, its Lebesgue measure is equal to 0. Okay, so these are all some of the examples that you can possibly look at. So this is the pullback of the open set alpha to infinity that we are taking, and then looking at what is the measure of that. What we are looking at is S is the set of all alpha for which this is equal to 0. So what is that? So here the set of all alpha for which it is 0 is going to be all numbers greater than 0. Okay. So for all alpha greater than 0, to see that this is going to be the measure of S is going to be 0 in this example. Okay, so we keep that example in your mind just to get the hang of what is going on. Now we are in a position to define what is the essentials of it. If is empty set, take T. If S is non-empty, then take beta to be equal to infimum of. So you are taking all those points for which this is mu of G inverse of alpha infinity is 0. There is some limit, and from there on it may not be. Okay. For example, I take a specific usual case, take the interval 0 to 1 as x. Now you take a function okay. Oh, sorry. We have been considering non-negative. That's enough for our purpose. This one. Now you see that if you take any alpha here, from alpha to infinity, pull back of that is going to be empty. Okay, but how far you can go? You can go up to this point. This point. Beyond that, if you take, see, you are going to get a set of positive measures. Okay, beyond that. So this is going to be the beta. Now this assumption that G is a map from x to 0 infinity included, gives an opportunity. It gives an opportunity to consider functions which take infinite value at some points also. Okay, right? So that is the whole idea. Now suppose on a set of positive measure, the function takes infinity, value infinity, then you are going to get beta to be equal to infinity. Okay, and if on the other hand, for some alpha it is going to be 0, and you are going for the infimum of all those alpha for which this is non-empty, for which this is, the measure is 0, I am sorry, measure is 0, then you are going to get beta to be the infimum of all such alpha's. Okay, so that is the whole idea. Now, since G inverse of G is equal to union n equal to 1 to infinity, G inverse of E, and each one of this is measurable for each n. So designate this is the definition of S by 1. Therefore, G inverse of beta infinity is the countable union of measurable sets. So what is that you conclude? This is measurable. Therefore, the countable union is measurable. Therefore, this is measurable. There is no problem. Okay. And if each of them has measure 0, then this is going to be a measure 0. Union of countable union of countable collection of sets of measure 0 measure 0 has therefore see that is measure of G inverse of theta plus 1 by n infinity is equal to mu of equal to measure of infinity, and each one is 0. This is equal to sigma mu of which is equal to 0. Because each one of this is going to be by the definition of beta. But then one more thing, if you take beta minus 1 by n, so note that the measure of beta minus 1 by infinity is not equal to 0. That is all. Okay. Or for any n without. That means you are at the brink of that. The beta that you are taking is at the brink of where this G inverse of beta infinity becomes. So we also observe from here so S is a set which contains the infimum of all these elements. We will keep that in our mind. And then beta is called essential supremum of G. This is the definition. It's the extreme value of alpha for which G inverse of alpha infinity has measure 0. That's the meaning. So beta is so you allow the function G that you consider also to take some value at infinity. I mean, at some places, infinite value. Okay, that's the whole point. So we want to consider such functions also, but at the same time, we want to define a number associated to each such functions, which we want to designate as, and this is designated. So for any f complex value, you know that mod f is real value. If f is complex valued and measurable, then mod f is going to be real valued, measurable, and it is positive. So you see that mod f is zero to infinity. So we can now write equal to supremum of, this is the definition of norm of infinity. Norm f p we have defined, and when p takes the value infinity, this is essentially the matrix. So this we shall designate like. So that's about the essentials. So now we define spaces like LP and L infinity. Okay. So we will separately write it down, although it's obvious what those spaces are, write it explicitly. Measurable, complex value, functions such that finite. This we shall basically, it's a definition. So L infinity mu is the space of set of all essentially bound. Okay, they may not be bounded. Bounded in absolute terms. Okay, essentially bounded, complex, this is the definition of L infinity. So we have defined what is LP and we have defined L infinity. Now, so remark, if f is such that mod f is less than or equal to lambda, for almost all x, if and only if that's a statement. So our norm f infinity is less than or equal. Okay, f is mod f is less than or equal to lambda for almost all x, then this is the situation. So that's a remark. A further remark that we want to make about is small l. So we have L infinity RK. These are the functions. And L infinity A is going to be set of all f bounded functions. Now, what happens to essentially bounded? Now, what happens is that if the bound is m, okay, then of course every bounded function is an essentially bounded function. But in this case, what happens is so note that deleted essentially bounded and replaced by bounded since the counting measure mu on A is positive for every non-empty that's the difference. Whereas in the general scenario, you have sets which are non-empty, still having the Lebesgue measure equal to 0. Like on R, take the rational point, is non-empty but has measure 0. Whereas if you take the set 1 to infinity, 1, 2, 3, etc. infinity, A as 1, 2, 3, etc. infinity, a countable set, and then you take any subset of that, any non-trivial subset or any non-empty subset of it is going to be the counting measure is going to be essentially the number of elements in that set. Okay? So it is going to be certainly positive. Now this is the statement that we make. Therefore, essential boundedness, if it is f is essentially bounded function on A, then f is certainly a bounded function. That's why we resort to that. So we shall rewrite the two inequalities, namely what is that? Holder's inequality and Minkowski inequality in terms of this new notation. Holder's inequality in this new notation. If this is the theorem that you have, conjugate exponents which means 1 by 3 plus equal to 1. And if LP and then FG, product of FG belongs to L1. And you have this is the form of the Holder's inequality. Now this means the following, that is, this is the Holder's inequality. So it is rewritten in this form, and quite often we will be writing. Now something that we have to prove here, I think I have left out here 1 less than or equal to P, Q less than or equal to. This is important. Now this is the statement of the theorem. Now we shall prove it. Just quickly prove. It is enough to just write it for this case. Particular scenario. This is five. This Holder's inequality. Now we have not explored the case when P equal to 1. When P equal to 1, Q equal to infinity. Or if P equal to infinity, then Q equal to 1. Okay. In that case, you have following. Let me put this number as 70. This talk today is I've forgotten that, but that doesn't matter. We are here for enough time. And let me okay. If P equal to infinity, Q equal to 1, that is Q equal to 1, then you have this is less than or equal. So, yes. So that is quite easy to see. Okay. This is of course almost everywhere X. Then what you have is the following. Now integrating the above inequality. Therefore, you have to see once again you see that it is when P equal to 1 or Q equal to 1, then P equal to infinity, or if P equal to infinity, then Q equal to 1, and you have this inequality valid. So this let us designate them. Thus, the Holder's inequality holds and 1 by P plus 1 by Q equal to 1. Okay. This is a crucial Holder's inequality. And what is the corresponding Minkowski inequality? That also let us write, and then possibly we wind up at that. It actually talks about the consequence of the Minkowski inequality. So this we write as, so we can easily do it. First take the case by Minkowski inequality. This is Minkowski inequality for these values. Okay, and that is essentially because to read this in this form, to observe this. F plus g to the power d2 is less than or equal to integral over x mod f and this essentially, so this is the Minkowski inequality. Keep this like this plus this is what we have in Minkowski, what we have proved earlier. So this is what we want to conclude. Okay. Now how do we do that? and this is less than or equal to and that implies that is true, or in other words, this is what you have. Now, this is only an intermediate step because we have earlier worked only for non-negative functions. That's the reason why we resort to this particular setup. Okay. Now we have to work out this for p equal to 1 and p equal to infinity. The two other extreme situations. So we take p equal to 1. Then you have mod f plus g mod g. Therefore, you have integral over x and that is so that proves it. Okay. Now we have to take the case for p equal to for p equal to infinity. You see that mod f plus g now taking essential supremum we get is less than or equal to infinity. Okay. So it's a matter of just taking the essential supremum on either side and using the usual inequalities. So that's about the Minkowski inequality, which is a crucial ingredient for proving that LP, the norm FP, is indeed a semi-norm to start with, and then upgrading it to the status quo. Let me do one more result. The next theorem is the following. Alpha is a complex number. See, all these statements imply that f g belongs to LP implies Now this is our objective for the situation infinite. So this has been achieved by for different cases we have considered separately. This is again simple to prove. So all that you observe, need to observe is this. Odd alpha f okay. Therefore now everything follows. Okay. So then you see that or in other words you have now this is for and for p equal to 1 this is again true. So you have this one, and again for p to infinity you will get then you have so use this property. Consequently you get so that completes it. So we shall need all these results to establish what is called the or to say that norm f p has the required properties of a semi-norm in the first space, and then with some kind of operations that we do, essentially get to what's called that. Thank you very much.